In the previous class, we obtained these expressions that relates the time derivative of a vector function beta with respect to a fixed reference frame with the same time derivative of the same vector function, but with respect to the moving reference frames that is subjected to rotational movement. We found that the expression that relates this times derivative is given by this expression. Now we are going to put into use this expression in order to perform the velocity analysis that relates the velocity of a particle as seen from these two different frames. In the previous topic, we obtained a result that relates the time derivatives of a vector function beta with respect to the moving reference frames and with respect to the fixed reference frames. The expression that we obtained is given by this cutout. In this part of the talk, we are going to assume that the function vector beta that we are dealing with is going to be equal to the position vector of a particle p. Using the equations that we obtained in the previous talk, we are going to find that using beta equal rp, the expression that we have is that the derivative of the position vector with respect to time and with respect to the fixed reference frame is going to be equal to the time derivative of rp with respect to time and with respect to the moving reference frame plus the angular velocity of the rigid body times the position vector. Okay? In this equation relates the velocity that the fixed reference frames observes in the particle with the velocity that the moving reference frames observes in the particle plus the angular velocity of the rigid body that is also the angular velocity of the reference frames times the position vector. This simple expression is enough to perform the velocity analysis of many mechanisms where the moving reference frames is located. A moving reference frames that also is subjected to rotation movement. A similar result can be obtained if we assume that the vector function beta now is the angular velocity of the moving reference frame. Okay, in this case, beta is equal to the omega, to the vector omega, and using the expression that we previously developed, let me just write it for reference purposes. It's going to be the time derivative of beta with respect to the fixed reference frames is equal to the times derivative beta with respect to the moving reference frame plus the angular velocity of the moving reference frames times the vector function. This is precisely the expression that we have written over here. However, we know that if we compute the cross product of a vector by itself, the result disappears. So in this particular case, we have that the time derivative of the angular velocity of the rigid body with respect to the fixed reference frames is equal to the time derivative of the same rigid body, of the angular velocity of the same rigid body with respect to the moving reference frames. This result is going to be interesting in order to be able to find out the relationship between the accelerations of a particle. In this part of the topic, we are going to assume that the vector function that we try to derive is going to be the derivative of the position vector p with respect to time and with respect to the fixed reference frame. Okay? And now we are going to find out what is the time derivative of that expressions. Over here we have the vector function beta given by these expressions, and we are going to derive again with respect to the fixed reference frame. However, from the previous results we obtained that the time derivative of the particle p with respect to the fixed reference frame is given by the time derivative of the same particle p with respect to the moving reference frames plus the angular velocity of the reference frames cross product the position vector rp. Okay? So according with the rules of vector calculus, we are going to take the time derivative of each one of the terms. Over here we have the time derivative with respect to the fixed reference frames of the time derivative of the position vector with respect to the moving reference frames. This is going to be another issue because the time derivative should be taken with respect to the same reference frames. We cannot process immediately in a straightforward way the time derivative of a vector function in two different reference frames. And in the second part, we are going to have the time derivative of these expressions. Now we are going to make some complicated calculations. First, we have to use this vector as the vector function beta, and this is going to be given by the time derivative with respect to the moving reference frame of the time derivative with respect to the moving reference frame plus the angular velocity of the reference frames times the time derivative of Rp with respect to time and with respect to the moving reference frame. These two terms that I have over here represents the time derivative given by this expression. Okay? Now we have to proceed with the other terms. Okay? Over here we are going to have the time derivative of the angular velocity times Rp plus the time derivatives of Rp, plus omega plus the time derivatives of Rp with respect to time and with respect to the fixed reference frame. Okay? Now, since we have that this time derivative as with respect to time and with respect to the same moving reference frames, this can be written as follows. This is going to be the second time derivative of Rp with respect to the moving reference frame. Okay. Over here, this I'm going to write to leave it without unchanged. It's going to be the time derivative of Rp with respect to time and with respect to the moving reference frame. Okay. Here I don't have any problem. The time derivative of the angular velocity of the moving body, that is also the angular velocity of the moving reference frames, is going to be equal the acceleration times Rp. Okay, and then we have omega times the derivative of Rp with respect to time and with respect to the fixed reference frames. But we know from the previous analysis that this can be written as follows. It's going to be the time derivative of Rp with respect to time and with respect to the fixed reference, to the moving reference frame. Okay, plus omega Rp. Okay. Then we need to proceed. We can notice that this term is equal to this term, And so we can write the following expression. This is going to be the second derivative of Rp with respect to time and with respect to the moving reference frame plus alpha, the angular acceleration of the moving body, that is also the angular acceleration of the moving reference frames, times Rp, plus omega cross product omega cross product Rp. In these terms, and this term over here, that is going to be the same, is going to be plus twice the angular velocity of the moving reference frame, that is also the angular velocity of the moving body, times the derivative of Rp with respect to time and with respect to the moving reference frame. This is the term that is usually called Coriolis acceleration. We are going to relate the expressions that we obtained we just obtained with the accelerations related to the problem of the rat escaping from the carousel. First, I have written these expressions since they are the time derivative, the time derivative or the time derivative of the reference frame is the same. This is just the second time derivative of the position vector of point P that we can imagine that is the rat with respect to the fixed reference frames. And the fixed reference frames will be the person represented fixed in this structure. Okay? So this term should be the acceleration that this person sees on the rat as the rat goes away or tries to run away from the carousel. Okay? This term should be the acceleration of the rat as seen for the fixed reference frame. Okay? Now, this term should be the acceleration that the moving reference frames represented by these persons sees on the rat. And in this particular case, this acceleration should be always along this line. Okay? Now, these two terms that we have over here represent something a little bit interesting. As the rat moves away from the center of the carousel, these two terms should most represent the acceleration of a point fixed in the carousel. That means as part of the carousel that in that particular point lies exactly below the rat that is moving away from the carousel. And finally, these terms represent the Coriolis accelerations. They don't have an easy physical interpretations. That we can see is that the Coriolis accelerations will always appear provided that we have two different conditions. The first condition is that the particle is moving with respect to a moving reference frames, and the moving reference frame is rotating. We have over here a rotating reference frames that is given by this person, and we have also the rat that is moving with respect to the moving reference frames. And provided that we have two conditions, we are always going to have Coriolis acceleration. Finally, I have to give some biographical information about Gaspard Gustave de Coriolis. Coriolis was a French mathematician and engineer that lived the period during the Napoleonic Wars and also the second French Empire. He decided he was a professor of the École Polytechnique, and he produces significant results. And the most important result that he obtained is precisely what it relates to the Coriolis acceleration. Okay.